Let's talk about dynamic programming. Dynamic programming, or DP, isn't just about filling up tables and getting the answer. Ever heard of the advice start with brute force solution to a problem? Well, before I talk about things like optimal substructure and overlapping subproblems, let us try to understand DP in much simpler terms. For now, think of DP, or dynamic programming, as just a better version of brute force, or brute force that is done right, or careful brute force, if you will. Let us try to apply this very idea with the help of a common dynamic programming problem. And I'm not talking about Fibonacci numbers here. Let's try to solve this problem, longest common subsequence, or LCS in short, using dynamic programming. The problem simply reads, find the length of the longest common subsequence, in short LCS, in the two given strings. Just to clarify, a subsequence is something like CAX. It need not be contiguous, unlike a substring. And a common subsequence would be CA and CA, for example. That is a common subsequence in both the strings. And the length of the longest common subsequence, as you might have already guessed, is 3. And that is CAT. So as you can see, this subsequence happens to be common, and it is the longest you can find in both strings. So how do we go about solving this problem if we had no clue about dynamic programming? Since subsequences need not be contiguous, iteratively generating all possible subsequences of length 1, length 2, and so on, and then seeing if they're common may not be a good solution. Let's try approaching the same problem recursively. Say we could take the help of two pointers. Pointer 1 pointing to the first character of the first string, and pointer 2 pointing to the first character of the second string. And say all we had to do for now is worry about the first characters. So I notice that C and M are different, and since they're different, they cannot contribute to my LCS. So I have two choices here. I keep my first pointer fixed and I move the second pointer, or I keep my second pointer fixed and move the first pointer. So I have two possible choices, and I try to get the best out of both the worlds. So when the characters are different, I have two possible moves, as I just told you, and I try to get the best out of both the worlds, and that would mathematically be just the max of both. What we are essentially trying to do here is we're trying to get the solution of the overall problem with the help of solutions of sub problems, that is, smaller problems. So basically, if I can figure out the solutions of these two sub problems, I have the solution to my original problem. And so let's try to solve for this sub problem and see how we go about doing that. So in this case, you can see that the characters that the two pointers are pointing at are the same. So that means now this will be contributing something to our answer. And what we can essentially do here is just move both the pointers ahead and add one to our answer, because the characters are common. So essentially, since the characters are the same, what I do is I move both the pointers ahead and then I add one. I just add one. So let us have a closer look to what moving pointers actually mean from the point of view of the strings. So if I were to move my first pointer ahead, keeping the second one fixed as it is, so that would mean I'm only interested in finding the LCS of ATXY and MCNAT. So that is, I'm no longer interested in the first character, and the second string is as it is. And similarly, in the other case, when I'm moving the second pointer ahead while keeping the first one fixed. So that means I'm interested in finding the LCS of CATXY and CNAT. So chopping out the first character. And this continues. If the characters are different, we take two routes again and try to get the best out of both the worlds. So as you can see, the path going this way would actually give us the best possible answer of 3. So since the characters are the same, the answer to this would be 1 plus moving both the pointers ahead. So that would mean just leaving on the first characters of both the strings. So that would be ATXY and NAT. And so what would be the LCS of ATXY and NAT? That would be LCS of TXY and NAT, or LCS of ATXY and AT. So whichever gives me the better one I pick. And in this case, it's going to be 1 plus TXY and T, because A was common, and that would be 1 plus XY and empty string. And if any of the pointers reach the end, so that means there's nothing left to traverse, and that the LCS of that would be 0. So overall, I'll be getting 1 here, 1 here, and 1 here. So if I were to add all that up, and that would be 3, and there is no other path that would give me a better answer than 3. So the LCS of the given two strings would be 3. So we apply the exact same steps to every single recursive tree out here. And what I'd like you to observe here is that we're doing a lot of work, and most of it is unnecessary. For example, LCS of TXY and CNAT is being calculated here as well as here, TXY and CNAT. So the same problem is being done again and again unnecessarily. And the strings weren't so huge, and say the strings were larger than the ones we had, and we can see that the amount of unnecessary work that's happening can get exponentially huge, and that can make our algorithm slower. So what can we do here? Like let me just give you one more example of unnecessary work happening. So to give you an example of another unnecessary work happening, so have a look at this. LCS of TXY and NAT, and LCS of TXY and NAT happening here as well. So that is a lot of work that could have been saved, and there's room for optimization here. So yeah, TXY and NAT, it's being calculated here as well as here. So wouldn't it be nice if someone just had the answer in some kind of a lookup table, or someone had it cached, and I could just and get the answer to that whenever I wanted to. So dynamic programming touches upon this very idea of avoiding unnecessary work and having to do that work over and over again. If I were to zoom out completely and expand all the paths, this is what my tree looks like. And as you can see, this looks daunting already, mostly because of the unnecessary work, that is repeated calls we're making. And it would definitely be better if we can optimize this a bit. And that is where dynamic programming comes into the picture. So any problem that can be solved using dynamic programming, it has the following two properties. That is, it has an optimal substructure, and it also has overlapping subproblems. So optimal substructure refers to that, we can obtain the solution to the overall problem by recursively solving for the subproblems. And if we can obtain the solutions to the subproblems, we can construct a solution to our original problem. So that happened to be the case with LCS. And as you've already seen, there were a lot of repeated calls and in LCS, and that could have been optimized. And there was a scope for dynamic programming to step into the picture. So that means there are overlapping subproblems, and so these two are properties for dynamic programming to be applied to a problem. And since our problem of longest common subsequence satisfied both the properties of optimal substructure and overlapping subproblems, we can actually use dynamic programming to solve this problem efficiently. So this is the recursive brute force approach to our LCS problem. And ing here are the 2 pointers. Initially, I'm calling LCS with 0, 0. That is the pointers pointing to the beginning of the 2 strings. And if the characters are same, that is they match, then I return 1 plus and I increment both the pointers. Or else I have 2 choices to make. I increment the first pointer while keeping the second pointer still, or I keep the first pointer still and I increment the second pointer, and I return the max out of both the choices I'm making. And if any of the pointers reaches the end of the string, then I return 0. That is the edge case I have to handle. And as you can see, on executing this code, the answer that is being returned is 3. And already told you that there is a lot of unnecessary calls happening, and the time complexity of this is exponential. And we can optimize this by making use of a memo. And if we do that, it's called memoization. And let's see the power of dynamic programming in action. So I call the exact same method with a memo, and you can also add a lookup table that is a matrix, and it'll work just the same. So here my key is with the 2 pointers. So if the subproblem is already calculated, then I just return memo key, or else I just cache it. So think of the memo as just a place to store your results. And if you are storing your results, then you're avoiding a lot of unnecessary calls. And that is it. By simply adding memo to the function, I'm optimizing this from an exponential time complexity to a complexity of big O of L1 into L2, that is the length of the strings. So let me try running this, and as you can see, the answer is still 3, and our code works. And if you were to use a DP table or a lookup table instead of a dictionary, the code would, or the logic would pretty much be the same. And this is how you would do it. So I'm adding -1 if I haven't stored the results already to that, and it's pretty much the same, and your code would still work. So let us try to now time it in order to get a better appreciation for memoization that we've used here. So when I time this with the lookup, this is our execution time. And if I were to comment this line of code that does the lookup, my time gets worse. And if I were to just add maybe just 3 or 4 characters, and the time should just get exponentially worse. And that is it for this video. And this illustration was just to show you that the time gets exponentially worse without the lookup, and the lookup just saves us a lot of trouble. So thank you for watching, and I'll see you in the next one.